The protocol called GRE, which is generic route encapsulation. You see, it's not encryption, it is encapsulation. The generic route encapsulation protocol, GRE, is a tunneling protocol. What is a tunnel? Let's say, okay, when I say tunnel, I remember in Istanbul. Istanbul is a place where two continents in one town you can see. One town, one place called Istanbul, but you will see two continents. Very rare to see such places. Usually you will have borders, strict borders with guns, but that is not the case here. Istanbul, the Turkey, if you see Asian side, European side, then there will be a bridge. And this is water. Very big ships also go through this passage, water passage. When I went, there was a Queen Victoria ship standing here, halted here. For 1 week I was there, I saw this Queen Victoria ship there. And the other side that you see is the European side. The side which is behind me is the Asian side. I'm in the cruise, I'm in a small ship. And this is that Queen Victoria ship which I was talking to you. This is 2015, August 31st. Right. This is the Istanbul Mosque. Once it was a church, and later, after the capture of Islamic, it became a mosque, and now it is a museum. It's neither a church or a mosque now. This is the bridge that I was talking to you that connects the Asia and Europe. Just one bridge. This is the bridge through which you can go from one continent to another continent. It's a beautiful place. Yeah, for training, yes. These friends were from Libya. This is Muhammad, I think Bashir or something. Forgot, these are all Libyan students. Oh, here is his name. This man's name. Yeah, this is Turkey, Istanbul. Roads of Istanbul. No, this is Dubai. Okay, so what I'm trying to say is, you saw the ocean there. I showed you a bridge. Now, don't focus on the bridge. You know, there is a train going under this. According to people, it's a water. No one knows that there is a train going under the ocean. Even if someone tries to go inside the water, all that they will see is only a tunnel, a cement tunnel. No one knows what is going inside. What is going inside is a tree, but no one knows which train at what time it goes, who are all going in. Nothing can be seen. But maybe someone who is swimming here deep under the ocean, adjacent to the tunnel, may feel that there is a train going, but they will not know what train, to what destination it goes, from which station it started, who are all going inside. Nothing can be known by the swimmer here. Same way. Consider this as a GRE tunnel. According to the intermediate network, this is the intermediate network. This is the original source network. This is the final destination network. According to the people in this intermediate network, it can be an internet, it can be a big ISP, it can be internet also. Many ISPs in between, many ISPs. According to the intermediate device, the traffic started from this end going to this end. That's all they will know. They will not know the original source or original destination. According to the people here, traffic source is this end, traffic destination is this end. That's all they know. How is this possible? What GRE will do is, it will take the original packet, which has got a source IP address, destination IP address, and it will encapsulate, see, generic route encapsulation. It will encapsulate with the address of point A and point B. So you're going to have a new packet kind of appearance. So the original packet becomes a payload. What is payload? The data that it carries. The original packet becomes payload. It becomes a data. The address is no more considered as an address. It becomes a payload. And this point A IP address and point B IP address, the tunnel IP address, becomes the IP header, layer 3 address. So according to these people in the middle between this tunnel and points, they see, okay, the packet needs to go to B, and they route the packet to B destination. Packet is coming from A, I need to forward it to B, they forward it to B. They don't have a chance of seeing this original header, original source and destination. This destination can be sometime a multicast address. It can even be an IPv6 address. But this tunnel is IPv4. You see? So the intermediate networks, they need a reachable IP address, which is encapsulated as an additional layer 3 and layer 2 header. In simple term, what I need to say is after GRE, it is no more 7 layer of OSI, it is 8 layer because you got additionally another layer 3. Based on the newly added IP layer, the packets are going to be forwarded. GRE works in layer 3. It's IP protocol. So IP47 is what? The GRE ID, protocol ID, IP47. Like you have for EIGRP, OSPF 88, 89. For GRE, it is 47. These are all IP layer protocol. And this is possible when you enable GRE on this point A router and point B router. So before all this, what we have to do is we need to identify those two routers between which you want to form a tunnel. It can be your edge router on two different sites, in two different sites. On the edge router, we create a virtual interface called tunnel interface. We create a virtual interface, a tunnel interface. Through the tunnel interface, we negotiate and bring the tunnel interface up. Yeah. So the negotiation should be successful to establish tunnel. For that, what we have to do is on point A, we have to give the correct reachable IP address of point B. And in point B, you have to give the reachable address, correct reachable address of point A. If both are reachable, then they can easily negotiate and bring the tunnel up. Once the tunnel is up, we have to tell on A and B what traffic should go through the tunnel. Only those traffic will get those encapsulation. So GRE, generic route encapsulation, is a tunneling protocol. This is providing a private connection between the sites. This original source and destination can even be a private IP address. Let's say here I have 10.0.0.1 and trying to reach 192.168.1.1. It is possible through GRE. Even though the internet cloud is a public network, this is public, 10.0.0.1 can ping 192.168.1.1 without any alteration of layer 3 header because the original header is being preserved inside as a payload. An additional layer 3 header, the address of A and address of B is what going to be used for routing in the public. For routing in the public, it is only A and B considered. A and B should be a reachable public IP address between these two sites. Inside, it can be anything. This intermediate device in the public, they don't see what is inside. They can see only the outer header and they route the packet. once it reaches the other end, this portion gets decapsulated, removed, and now the payload becomes the header. Once the encapsulation is removed, the original destination is revealed and the packet is delivered. Yep. So GRE is used in various places. This is one example. I want a private to private connection. I don't want natting. I don't want natting. I don't want any address change. I want to reach my remote private network. It is possible when you form a tunnel between the customer edge routers. Form a tunnel. To form this tunnel, you don't need to get any approval from ISP. Simply, it's your own router. Your router has got this protocol. You have public reachability between two sites. Using the reachability, you can negotiate tunnel, and you can talk to the remote office with your own private IP address without doing any alteration. The other example I showed you is you have IPv6 in your sites and you want to transport this over IPv4 network. There also you can use GRE. The other example I said is you can also send a multicast traffic so that you no need to have this multicast enabled on all the routers in the intermediate router. You no need to enable that PIM. Like this, even in the security world, we enable this so that I can add IPsec to this and make it as a encrypted, not just encapsulated. I also do encryption to this packet. That's IPsec. GRE is not going to provide you security. It provides only tunnel. Don't say it is a secure tunnel. It's a private tunnel, but it is not guaranteeing you any security. It is not encrypting. It's just an additional layer 3 encapsulation. It is not encrypting the payload. It is just encapsulating. But when you add IPsec to this, only then it becomes secure GRE, IPsec GRE. That's another protocol. So today we are going to now see a demo on GRE. Let us take like 5 routers. The private network will be behind R1. So which is 10 dot, let's say 1.0.1/16. I want reachability between this private network to this remote private without me advertising this network. These ISPs, definitely they won't route any private destination traffics. They don't, because they don't know. They won't have routes to outside private networks. So we will not be doing natting, but we will be successfully pinging between this loopback to this loopback after we finish GRE configuration. Right, so we have to quickly configure this basic things like IP address and routing between R3. I should say I have to route between R1 to R2 public IP address. So I'm also going to run OSPF here. Because ISP only needs to provide reachability between public to public. So I'm going to have it. Or I can have a default route to R3. Anything is possible. You can do any one of this. Then I can have a static route on R1 pointing towards R3, or run OSPF up to R1 and R2. So as I say, I'm going to write a static route on R1. IP route. Okay, default route. Send the traffic to 20003. This is for tunnel formation. See, R1 should ping R2. Otherwise, tunnel cannot be negotiated, right? So I have to do this like way, or I should write a static route saying 25000 network. Send it to R3. Usually in the real world, we don't write like that. We don't write 25. We don't write 25 here. We write default. So let it be like real words. And write to memory. So this is what will go on R1. And let's finish R2. Then we will go to the other routers. R2, let's get the console. R2 console is ready. The configuration loopback will have 2.1. And this is going to have 25.2. The default route will be 25.5. All right. We will write another static route later after forming GRE to say what all traffic should go through the tunnel. Right? So that's later. As of now, these two routers are ready. Let us go router 3 configuration is no loopback needed. I don't want loopback. F00 will have 20.3. And here I would like to run OSPF, IP OSPF 1 area 0. And the interface F0/1 34.0.0.3. I'll remove this. That's all. So this will be more than sufficient on R3. And on R4, F00 will be 45.0.0.3. 26.4. F01 is 34.4, or 4 is also over. Now on R5, F00 is 25.5 and F01 is 45.5. And this goes on router 5. It's done. Okay. Now I want to check the reachability between 5 and 3 to start. 20.00. Hold on. I can ping and see from R1 to R2 itself directly. Because I got a default route. Ping 25.0.0.2. It is pinging, which means your OSPF is good in the middle. Your static default route is also good. Now, only thing is left is GRE configuration, right? We're going to see GRE. It's very simple. You see, interface tunnel 0. This tunnel needs a private IP address. Okay. Tunnel needs one private IP address. I say IP address 10.3.0. or 192 to make it interesting for you. I say 192.168.0.1. This is for the virtual link that we are creating. That is how it should be, because if you put a public IP address, you are wasting an address. It's a private tunnel. Why you want to put a public IP address and waste it? Only two. Tunnel is having only two ends. Okay. Now, tunnel source is what? 20.0.0.1. What is the tunnel destination? 25.0.0.2. So when I put this address, it will try to go and negotiate with this address. It will go and negotiate to this destination. And then tunnel mode is an optional one, because by default it is GRE, but I'm just showing you tunnel mode GRE IP. You no need to say this, it is default. That's all. This side is over. Let's go to the other side. Interface tunnel 0. IP address is 192.168.1.2. 255.255.255.0. Tunnel sources. You can say 25.0.0.2, or you can also say this one. Tunnel destination is 20.0.0.1. All right, that is all. I'm not saying more because that is GRE by default. If you want, I can show you. Show interface tunnel 0. You can see GRE IP as a default transport protocol. Now, if you see, you can ping 192.168.1.1. Oh no, 192. So if this ping happens, it proves that your tunnel is good. Did I give 1.1 on the other side? 0 dot. Okay, I put wrong. That side I have put 1. Let me put tunnel address as 0 dot 2. It's not one network, different. Hmm. Now I should be pinging. You see, none of this middle network knows about this 192. We did not advertise this in OSPF. We are not running OSPF on tunnel. You see, show IP OSPF interface brief. We are not running OSPF at all in this router. None of the router in the middle knows what is 192. If you want, you can go and check. Show IP route. They don't have any route. 492, no routes. 10 network, no routes. So the tunnel is up. Already you are able to ping the remote end of the tunnel, 192.168.0.2. Now all that we need to do is pass the traffic through the tunnel. I'm going to say IP route. If you are going to 10.2 network, then send the traffic to via tunnel 0. Simple. Send the traffic via tunnel 0. Likewise, go here and say IP route. If you're going to 10.1.0.0 network, send the traffic via tunnel. That's all. If you have done this, you will be able to ping via tunnel 10.2.0.1 source loopback 0. You are pinging. If you want, you can trace route and see. When you trace it out, you will see only one hop because the other things are tunnel. And now when you capture a packet using Wireshark, you will see the double header, layer 3 header. Okay, I'm going to ping again. I'm going to ping again from R1. You see ICMP echo request and reply. You see this is the original header which has been encapsulated by GRE, generic route encapsulation, and this is the upper header, the new header, the tunnel address. Yeah. So you see, but the payload is not encrypted. This is not a IPsec. This is only encapsulation. GRE. GRE. Yes. All right. So that's all about GRE.